Hey there, Calculus 2 students. I'm recording in my garage a new video using some screen capture today. This is going to be an introduction to plotting points with polar coordinates, and I'm using the Desmos online graphing calculator to help with this. Some of you may have learned about polar coordinates in a pre-calculus or trigonometry course before, and then hopefully this is just a helpful review. But there also may be some of you in my calculus class who have never before seen or used polar coordinates, or at the very least could use a refresher. And so I hope this does the trick. So the first thing we need to understand is plotting points. And so I've got a point I've just plotted on here on the normal, you can see the normal x and y axes. But we're not going to be using the x and y coordinates to do this. So let's label this point with a couple new numbers. And you can see that those new numbers, 4.8 and 0.8, are over here on sliders on the left part of the screen. And I will provide a link to this to allow you to play with this same graphing calculator exercise. But as I toggle this r and this theta, my point is moving around in different ways. Okay? And those numbers do not refer to x and y coordinates. For example, here we expect the x coordinate to be close to 0, right? And that's not really reflected in those numbers. So what do these numbers actually represent? So whenever we plot a point using polar coordinates, one of the first things that we do is figure out, instead of how far to go over and up like we do with Cartesian or rectangular coordinates, what we do instead is try to figure out the direction in which we want to go, and then how far to go. And so here I've got what I'm calling a direction line from the origin that tells us how do we travel from the origin to our point. And that is going to be reflected by the angle, which is what theta represents. So the angle is measured from the positive x-axis like we've grown used to. And as I increase theta, I can see my line rotate accordingly. Now I can rotate beyond 2 pi, in which case I'm going to lap myself. And I can also use negative angles to rotate in the clockwise direction. Now once we have our direction established with theta, we use r to represent how far we're going to travel. So let's get rid of the entire line and just reflect the distance we're going to be going from the origin. And so that's what the r value is. And typically we are going to use the notation r comma theta, which I actually find a little counterintuitive. I always wonder why we don't list the theta first, because it is typical for us to compute theta first, and also to use theta as an input and r as an output, in the same way that we use x and y as input and output respectively. But for whatever reason, our convention is to first list the r value and then the theta value. And this theta is going to be in radians. Okay, everything in calculus we do radians, not degrees. And you can see as we change the angle theta, we're changing the direction. And as we change the r, we're changing the distance from the origin. Now we should point out that we can use negative values of r, in which case we are going the opposite direction. Okay, I probably need to at some point fix this angle, because the angle is still measured according to this direction line in the other on the other side. And so we're actually still talking about the same angle, let's say an angle of like 1.1 radians. Okay, but with a positive r value, we're going this direction. With a negative, we're going the other direction. And so I'm just now noticing that that blue angle marker is a little bit different than what I would like. Okay, well, ignoring that for the moment, let's compare this with our Cartesian label. So here I've got the x and y coordinates as you expect them. So on top I have r theta, on the bottom I have x and y. And of course we know what those mean. If we get rid of our polar labels for a second, we can see the x and y as distances from those axes with a sign as needed. So if I move to another quadrant, for example, I can see the y becomes negative, or the x becomes negative, or both. Okay, so this is our rectangular coordinate system that you're used to. If I put them both back, we can see how the x and the y and the r are going to form a right triangle. And that's going to be useful for establishing our conversion between these systems. So if I want to convert from polar to Cartesian, remember from our trigonometry that then x is going to equal r times cosine theta, and y is going to equal r times sine theta. And so if you're given the r and the theta, you can plug them into these formulas to get your x and y respectively. And so whenever r is 4.2 and theta is equal to 7, well, maybe we can back that off to be more reasonable. Let's say theta is equal to 0.8. Well, then your x is going to be this 2.926 business, and your y is going to be 3.01, and so on. And so you can compute that by finding the cosine and the sine of 0.8 and multiplying by your r of 4.2. If you want to convert the other way, using that right triangle, you can notice that r squared is the same as x squared plus y squared. And so that gives you a way to compute r. And likewise, the tangent of theta is going to be the quotient of r sine theta and r cosine theta, which is y over x. And so if you know x and y, you can use those to find r squared. But then you have some options. R could be plus or minus, and tangent could be referring to a variety of angles as well. And so in our next video, we can explore how polar coordinates are not unique with some computation. For now, however, let's take a look at, maybe let's get rid of our Cartesian label stuff for a moment and remind you that if I rotate more than 2 pi, I can get back to where I started. And so the same point can be represented by 2 different angles with the same radius. On the other hand, if I rotate a half angle but use the negative radius, then I can also represent the same point. And so one major difference between your polar and your Cartesian coordinates is that the polar representation of a point is not necessarily unique. Okay, so I will provide a link to this Desmos online graphing calculator exercise to let you experiment with what polar and Cartesian coordinates mean. I also point out here that in the settings you can actually change from a Cartesian mode to a polar mode. So if I have a grid here, you can see the normal rectangular grid that you're used to, but I can switch that to what we call a polar grid that emphasizes the distance from the origin with concentric circles as well as the angle of rotation. And so as I change the angle here, you can see it overlapping those various lines. And when I change the radius, you can see the circles nested within each other. Okay. All right, I think that'll do it for now. So we'll stop this short recording and move on to another.